Rational functions. So let's first define what a rational function is. R of x is equal to p of x over q of x, where p of x and q of x are polynomial functions, i.e. P of x and q of x are of the form a sub n, I did that twice today now, x to the n plus a sub n minus 1, x to the n minus 1 plus plus a sub 1, x to the 1, but we don't write the 1 because x to the 1 is x, plus a sub 0. And, that's an and, q of x cannot equal 0, meaning I can't have 3x plus 2 over 0. There are going to be times when the denominator function is equal to 0, which in fact is part of what all this is about. So in the end, with regard to rational functions, we want to know what they look like when I graph them, or I think of it as what is the nature of that rational function. So I want to know when I graph it how it actually appears on the graph. Does it look like this or something else? And how we determined how rational functions appear to us when we graph them is by determining the locations of asymptotes. Okay, so now there are two types of asymptotes. There are three types of asymptotes. Three types. There are vertical asymptotes, horizontal asymptotes. That's an R, not a Z there. Horizontal. So how about horizontal asymptotes? And then there are, I guess maybe there's even 4, because it depends on how you chop them up. Oblique or slant asymptotes. And then there are curvilinear, if you want. I would say curves. Curves themselves, right? Okay, so they can be curves, or these are all straight. Those are all lines, and then you have everything after that. You can have asymptotes that are cubics and quadratics, etc., but that's a whole separate thing, which we kind of need to... Well, I'll show you an example if we have time. I don't want to make this video too long. It's already going to be longer than you desire, I am certain. So in addition to that, so you can see this is multidimensional. Those different types of asymptotes, when do they occur? Well, they occur in different situations based on the rational function itself. But then we also have 3 different ways, I would say at least. I'm going to highlight these 3 different ways to think or consider the rational function. Okay, so I'm going to do the first way, which is by identifying these circumstances or rules. And that's typically what's in every textbook, and plenty of students fall back to that. There's a way to think about rational functions in terms of limits, which you may or may not be familiar with. I'll go over that quickly. And what I really want to emphasize is to just think about them as division, since with a good portion of this module or unit is about division of polynomials. So we'll get into that, and that's why this topic falls into this area almost in every textbook. So let's do the rule thing first. We're going to do all the quote rules or circumstances that creep up for rational functions. But one thing let's do first. No matter what the circumstance, the determination of a vertical asymptote is the same every time. Well, you can't read the letters, can you? A-S-Y-M-P-T-O-T. Vertical asymptotes. Vertical asymptotes are determined from the denominator. So again, if I have this P over Q, I could have something like this, 3x squared plus 17x minus 2 over x minus 7. And so a vertical asymptote will occur when this denominator goes to 0. Why is that? Well, if I put 7, for instance, if I take the denominator and set it equal to 0, and then solve that denominator, I get x equals 7. So at x equals 7, for this particular situation, we have a rational function as undefined. Why is that? Well, r of 7 is equal to 3 times 7 squared plus 17 times 7 minus 2 over 7 minus 7, and of course my denominator is going to 0. So any number divided by 0 is undefined. I don't know what it means. So when I say undefined, it means exactly that in English language. If I said some word that you didn't know what its meaning was, for you, that word is undefined. So that's what I'm getting at. We don't know what this means. Mathematically, we do not understand what that means. So it is called undefined. And when it's undefined, I can't plot anything. For instance, at x equals 7, my function is undefined. How do I plot that on the x and y coordinate or the coordinate plane? I go to 7, and I go to try to plot a point, and I can't do it because I don't know where undefined is located. So we often represent vertical asymptotes with dotted lines. And so this also tells you that asymptotes are functions. That's not true. They are equations, because right away this vertical one is not a function, right? Asymptotes are equations, and so in this case it's x equals 7. It's exactly this. When we set it equal to 0 and solve for x, it's x equals 7. This is a vertical line at x equals 7. Okay? Now, there is a particular situation, for instance, that we need to be aware of, and my suggestion, I previously treated this differently, and I believe it's to your benefit that you treat it in a better manner, which is why I'm redoing this video, because I have a previous video made. So let's go back. We're still sort of talking about vertical asymptotes, but a special case. I want to reverse this idea of a special case. So let me give you this other example. So this is like example 2, I suppose. And let's say that my rational function is equal to x plus 3 times x minus 2 over x minus 2. And what I want to point out is, yes, if we were trying to determine the vertical asymptote, we would just take x minus 2, set it equal to 0, and that gets us to x equals 2. So I'm picturing this idea. At x equals 2, I have this vertical asymptote at x equals 2. But what's happening here, if you look closely, is I have this in factored form. Typically, you wouldn't see that. You would see this. R of x is equal to x squared minus x minus 6 over x minus 2. So it wouldn't be so obvious to you. I made it obvious because he wants you to see it. What happens to this x minus 2 divided by x minus 2? I'm hoping you're saying it divides, so it's equal to 1, or in the least you could say that it cancels. So when I cancel those, I get this. R of x equals x, what did I have? X plus 3, right? Oh, and that should be plus 1x. I have x plus 3, right? But because my original function was all of this, or if you prefer all of that, it's really, my rational function can be that. It's just a different way to write these. These are equivalent if I add this information. X cannot equal 2. Okay? Then it's telling me what's really happening here. So this, to us, looks like one of these crazy things. But this particular one, because I have this factoring, canceling, equaling 1 type of thing, it is not one of these with an asymptote. This function actually, which is the same as this one, right? X squared plus x minus 6 over x, what did I have? Minus 2, I think? Yeah. These two, this function and that function are the same, just written differently. It looks like this. it looks like x plus 3. Looks like this line. It looks like y equals x plus 3. It looks like that line, except it at x equals 2. Let's say that that's right about here. At x equals 2, it has what is called a hole. In casual conversation, it's either a hole, and they use that word in calculus, but I prefer the more mathy phrase, a removable. You can pick one, it doesn't matter to me. Removable discontinuity. So as many of you are heading off to calculus, that hole is also called a removable discontinuity. Okay? So why is it a removable discontinuity? Because I can remove it. Either you can say I can just pluck it right out of that line, or I can remove it because these two factor out and I can just remove it from the equation. When you start talking about limits, when you start out calculus, that's what you're going to hit very early on. So you have this removable discontinuity. And the removable discontinuity, or hole, is that, I think I need to hit pause here because I have a cat jumping in my... So, removable discontinuity and hole, and so your function ends up looking like what's left after you remove the discontinuity. So this particular situation I used to treat as a special case, and I think it'd be better if I didn't and just had us check for that, or suggest that you check for that first thing whenever you're dealing with the rational function. Okay? So that's taken care of. So now let's go look at these, quote, rules or circumstances. I'm trying to scoot up here. I don't need to scoot up there. Okay, so let's write this out up here. The rational function, as I defined it, p over x, p of x over q of x. Oops. But I'm going to write it out this manner so that we can use these values. So a times x to the m plus, and of course it can be that whole polynomial, right? So there's more after that, possibly, over b times x to the n plus, and there could be more stuff. So when I'm saying that, I'm thinking like it could be 3x squared plus 2x minus 5, and this could be 2x to the 7th plus 3x squared plus 2. And so in other words, I'm saying there could be more stuff after that, but my focus is really on these two lead terms. And so that's what I've written out there, so we can reference those letters, because those letters, A, B, M, and N, are going to be part of our scenarios, our how we determine the characteristics of our rational function. Okay, so scenario 1 is when, let's remove that. So scenario 1 is if m is equal to n. So I'm saying that if the two polynomial functions are of the same degree, whether they're both quadratics with squared lead coefficients or cubics or whatnot, if they are the same degree, and that should be an if m equals n, then my non-vertical asymptote is y equals a over b. When I say non-vertical, in this case, it is in fact horizontal. The asymptote is in fact horizontal because it's going to be y equals a over b, the ratio of the lead coefficients. So my example, I think this is example 3 at this point. Let's say my rational function was x plus 2 over x plus 3. Hopefully you can see, oftentimes problems are going to ask you to find the vertical asymptote. I'm suggesting you find the vertical asymptote, what it might be. That would be x plus 3 equals 0, so I'm going to have x equals negative 3. And then I have to determine, does that, is this denominator a factor of the numerator? Hopefully you can see that x plus 2 is not divisible by x plus 3, so no, it's not a factor, so I do not have a removable discontinuity. So I do have a vertical asymptote at x equals -3. And the horizontal in this case, asymptote, is y equals the ratio of the lead coefficients. In this case, I have 1 over 1, which is 1. So y equals 1. So if I go to graph what this looks like, and my line's a little off, but that's okay. I'm going to have a vertical asymptote at x equals -3. And I'm going to have a horizontal asymptote at y equals 1. Oh, I don't want that color. Y equals 1. I didn't want that color. Okay? Now, I'm not aware of any better way to figure out, does this look like this? Does it look like this? Does it look like that? Or does it look like this? Okay? It wouldn't cross. My best way, and I've talked to other instructors and they tell me the same, is I'm going to choose a number, typically an integer, that's close to my vertical asymptotes. In this case there's only one, but there could be more than one. And I'm going to put those numbers into my equation and figure out where they are located with respect to this y equals 1. So if I take r of -2, put -2 plus 2, -2 plus 3, and I get 0 over -2 plus 3, which is 1. So I get 0. So at -2, x equals -2, I get 0. So I have a point right here. And then if I put in r of -4, I get -4 plus 2 over -4 plus 3. And I get -4 plus 2, which is -2, over -4 plus 3, which is -1, and I get 2. So this, at x equals -4, I have a value of 2. This is telling me that my graph looks like this over there, and it looks like this on the right-hand side of my vertical asymptote. And so my function looks like that. Okay? So that's scenario 1. So that's what it looks like. And we have to go to a different example. So that's if m equals n. Okay? So remember, we're still looking at this thing. I'll rewrite it on the next part here. So remember, it's r of x equals a times x to the m over b, doofus, x to the n. It could be a much bigger polynomial, but we're really interested in looking at this first term. So in situation or circumstance 2, it's if m is less than n, then we also have a horizontal asymptote. Then the asymptote is horizontal, and is y equals 0. Okay? Now, so let's get an example. Again, I think this is 4 now, maybe. Yeah, something like that, 4. And so I'm going to have r of x equal to x plus 7 over x squared plus 2x minus 3. And so typically first we go for what is the vertical asymptote. And we will have this polynomial, the denominator, we're going to set it equal to 0. And then we're going to solve it. Now, you have multiple ways to do this. You can use the quadratic formula if you wish. You can just solve it, which you can't do with this one. But if you had like x squared minus 4 equals 0, you could just solve it by adding 4 to both sides and then taking the square root of both sides and getting x equals plus or minus 2. But we can't do that in this particular case because we have a trinomial. And so a third way is to factor. And so if I factor it, I get x x minus 3, x plus 3, x minus 1. And so x plus 3, x minus 1 is equal to 0, which means that my vertical asymptotes occur at x plus 3 equals 0, which is at x equals negative 3, and at x minus 1 equals 0, x equals 1. So I have two vertical asymptotes, and they're at x equals negative 3 and x equals 1. All right? So let's keep that in mind. Now, were either of these two a factor of the numerator? They weren't, so we didn't have a removable discontinuity. Okay? In fact, this particular situation, we wouldn't have a removable discontinuity because we would never get to a function that was not in the denominator. But that's a whole complicated thing, so we'll deal with that in a second. Or we won't deal with that. It's not a situation you're going to encounter. We typically do not put removable discontinuity, so we'd end up with 1 over x plus 2 or something like that. Okay? Not in this course anyway. So, what about my horizontal asymptote? In this case, it is horizontal because the degree of m is 1, the degree of n is 2, so m is less than n, and so my horizontal asymptote is at y equals 0. So taking all that information into account, I'm going to have my function, my asymptotes graphed. They're going to look like this. Y, I think I said negative 3, so let's make that over here. And I said 1. Let's put that here. That's x equals 1 and x equals negative 3. I believe that's what they were. Scoot up there. Yep. And then we had y equals 0. And so y equals 0. And how do we determine what our function looks like? Again, the best method that I'm aware of is to choose numbers that are close to my asymptotes, and those numbers are x equals negative 5, x equals negative 3, x equals negative 4, and x equals negative 2, x equals 0, and x equals 2. So if I substitute those values in, let's do this as quickly, not too quickly, but as quickly as possible. Negative 4. I had, what is it, x plus 7. So negative 4 plus 7 over x squared plus 2 times x minus 3. Let's make sure that I got that correct. Plus 2x minus 3. Okay, so I'm going to put a negative 4 into each of these places. I'm going to get negative 4 plus 7, which is 3. I'm going to get 16 minus 8 minus 3, which is 3 over 16 minus 11 is 5. So 3/5. Is that greater than or less than y equals 0? That's greater than. So at x equals negative 4, I'm at 3/5, so somewhere in here. So that's telling me that this part looks like this. Let's go over in here and do this x equals 2. So I did that one. Let's do this one. So if I'm working on x equals 2, I'm going to put 2 in here, 2 in here, and 2 up there, and I get 9 over 4 plus 4 minus 3. So that's 9 over 8 minus 3, which is 5. Is that greater than or less than 0? It's greater than. So it's 9/5. That's almost 2. That's closer to 2. So I have a function over here that looks like that. Now let's do 0, because that one's easiest of the remaining 2. And so let's do that. X equals 0, 0, 0, and 0. And so I get 7 over negative 3. That's negative 7/3. I really need to know whether it's greater than, above the horizontal axis, horizontal asymptote, or below the horizontal asymptote, which happens to be y equals 0. So that one's negative. So at 0, I have this negative 7/3. It's really down here, I guess. And then lastly, I'm going to work on this negative 2. So negative 2 goes in here. Negative 2, negative 2, negative 2. Up in the numerator, we get 5. 4 minus 4 minus 3, and so I get 5 over negative 3. So that's a negative number. And so that's down here, negative 5/3, something like that. So we have this. Now, is it possible that we end up having something like this? Yes, but we're not going to give you problems that get all kinds of crazy, or at least too crazy. We want to make it a little as straightforward as we can in the context of doing this. So that's the second situation where the m is less than n. M is less than n. Okay? Now, scenario or circumstance 3. Again, we're still working with r of x equals a x to the m and b x to the n. But in this case, we're looking at circumstance or scenario 3 where m is greater than n. So the numerator has a greater degree than the denominator. And so example 5 is r of x, and I didn't write one out for this. So let's say 3x squared plus 2x minus 1 over x plus 2. Okay? So first, vertical asymptote. Well, that's going to occur at x plus 2 equals 0, which means that it occurs at x equals negative 2. So I have a vertical asymptote, maybe, at x equals negative 2. Now, is x plus 2 a factor of the numerator? Remember, we have to check that to see if it's a removable discontinuity or not. So, again, there are multiple ways to do that. We can either factor the numerator. Ooh, this has got a 3 in the front, so it's factoring by grouping. Or we can use synthetic division if this is a binomial, or long division if it's not. It's a binomial that has a root of negative 2, so I'm going to use synthetic division to determine if this is a factor of this. Since I just pulled the numerator out of my tuchus, I doubt that it is, but who knows? Maybe I got lucky or unlucky depending on what your desire is. So I'm going to bring this 3 down. Negative 2 times 3 is negative 6. Negative 6 plus 2 is negative 4. Negative 2 times negative 4 is 8. And so I get 7. There is a remainder. That means that x plus 2 is not a factor of the numerator because x plus 2 doesn't divide the numerator. So I do not have a removable discontinuity. And so I know that my function looks something like this with a vertical asymptote at x equals negative 2. Now, what is happening with the other asymptote? Well, it's not horizontal. It's not horizontal. This particular one, if m is greater than n by exactly 1, in this case it is 2 versus this 1, right? It's greater by the amount of 1. So 2 is greater than 1. There's only a difference of 1. Then I have, if there's only a difference of 1, then I have a slant asymptote. Sometimes it's called an oblique asymptote. Oblique. Okay? Which means it's a line. It's a slant line. Okay? How do I determine what that is? Well, you have to do the division. This is going to be the slant asymptote is y equals the quotient, the result of division. So we're going to go back and do that synthetic division because we can. Remember, we use the root, so it's negative 2, and it's 3, 2, negative 1. We'll do it quickly because I already did it once before. So 3, that's negative 6, and that's negative 4, and that's 8, and so that's 7. I have a remainder of 7. So let's look at the division algorithm. I have 3x squared plus 2x minus 1 divided by x plus 2, and that is equal to this quotient, right? 3x minus 4. My remainder is 7 over that divisor. This, remember, from the division algorithm, is your quotient. This is your quotient, the result of division. So is that. And so my asymptote is y equals 3x minus 4. So if I go back to my graph, it is 3x minus 4. That means it has a y-intercept of negative 4. Yeah, it has a y-intercept of 0, negative 4. Let's use blue. 0, negative 4. It has a slope of 3, so I'm going up 3 and over 1. Up 3 and over 1. So my line looks something like this. I'm sorry, it's not a line, it's an asymptote. I don't want to use that color. I want to use this color. I can't make a dotted line that nicely. Not with the, that's what I was trying to do, is make that line. I need to bring this all the way down, and I need to do this with this. So remember, that's an asymptote. It's not a graph. It is not the weird situation where I have removable discontinuity. My function, its asymptotes look like that. All right? Now, what does my function look like? Again, like I said previously, I'm going to choose numbers. Oops. I'm going to choose numbers or values that are close to my vertical asymptote. In this case, it's -1 and -2. So, -1 and -2. I'm going to erase this so I can be near my graph. Hopefully you captured all that or took notes. X equals -1 and x equals -3. So, my rational function at -1 is equal to 3x squared plus 2 times x, let me say -1, and x plus 2. So I'm going to put a -1 in here, -1 over there, -1 over there. And I get 3 times 1 minus 2 times 1. And -1 plus 2 is 1. 3 times -2 minus 1 is 0 over 1, which is 0. So at x equals -1, I get a 0. I get a point right there on the x-axis. So now I'm going to try -3. So -3, -3 squared is 9 times 3 is 27, minus, it's a -3. 2 times 3 is 6, negative, minus 1. -3 plus 2 is -1, which means I have 27 minus 6, which is 21. Minus 1 is 20 over -1, which is a negative number. But it's a -20. So -20, where's -20? Well, it appears to be below this slant asymptote. -1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it's down here somewhere, okay? I don't know exactly, but what I want to do is double check that it is below that value. So what was my slant asymptote was y equals, and I erased it, didn't I? I want to say it was 3x. So at x equals -3, what does that equal? Why? Because I want to know the exact where this line crosses, what's its y value, at that same x value where I'm looking at the asymptote, or looking at the function. So this turns out to be -9 minus 4, which is -13. -20 is below -13, so I'm down here. So my function looks like this. It's below the slant asymptote, but it's to the left of my vertical asymptote. And on this side, it is above the slant asymptote and to the right of my vertical asymptote. So it looks like that. Okay? So let's look at these rules in summary. If I have a rational function and it's defined as a polynomial divided by another polynomial, and it would look like ax to the m plus whatever's left over or extended over b times x to the n. So circumstance 1, well, let's do this in summary. So the vertical asymptote is where denominator equals 0. So they're at x values, x equals where the denominator equals 0. And then scenario 1, or circumstance 1, is when m is equal to n. Then non-vertical asymptote is A over B. And scenario 2 is when m is less than n, then non-vertical asymptote is y equals 0. And scenario 3, when m is greater than n, then non-vertical asymptote is y equals the quotient. You actually have to do the division. You can't rely on anything else. You actually have to do the division. Whether it's synthetic division or long division is dependent on what the denominator is. Okay? So that's what we're talking about with regard to a summary of the, quote, rules or circumstances. Remember, always check. So let's put this down here in red. Always check for the removable discontinuity first. Okay? Or right after you do this. Okay? Removable discontinuity. That's what I would say. Used to not say it that way, but I'm saying it now. Now, there are other ways to view this whole thing. Okay? So let's look at them. Let's look at those same examples. So let's crawl back up into our examples. I'll erase around them and we'll look at them again. Let's say rational functions. That's where I define them. 3 different types, blah, blah, blah. Here's our first. That was that. We don't need to worry about that. Here it is. So here's the first one where m is equal to n, right? So let's erase around this. And all the bottom stuff, all the, graphing it and figure out where it's located, is it above or below the horizontal asymptote? That's all the same. All I'm suggesting is there are different ways to think about the non-vertical asymptotes. So this is called looking at it with regard to the limit. Okay? And here's how we figure out the limit. You imagine my rational function as x approaches infinity. So as x gets really, 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 really big. So in other words, I can think of it as r of x and substitute infinity in for x. You can't really do that. It's just a conceptual exercise because infinity is not a number. But if I think about a very large number, plus 2, and a very large number that's equivalent to the one up the top, and add 3, if I had let's not even write out a bunch of zeros. Let's say I had 10 to the 107 plus 2 over 10 to the 107 plus 3. This 2 and the 3, aren't they close to being inconsequential, if not inconsequential? They're so small or so little compared to 10 to the 107. Imagine 107 zeros after the 1. That 2 ends up not mattering very much, does it? These two numbers are essentially the same, and I get 1. Now, if I had a constant, instead of my example where I had 1 and 1, let's say I had 3. Let's say that my rational function was 3x plus 7 over 2x, right? Then I'm getting 3 times some 10 to the 107 plus 7 over 2 times 10 to the 107 plus, or there's no number after that. Well, this 7 becomes inconsequential, but this one is still 3 times that 10 to 107, 10 times 10 to the 107. This is 2 times 10 to the 107. So when I cancel all this stuff out, see, I get 3 halves. The 7 gets artificially canceled out, if you wish, because it's inconsequential to the size of the number. It doesn't matter anymore. The numbers are so huge that the 7 doesn't matter anymore. Okay? I'm over by infinity. So infinity divided by infinity becomes 1. But 3 infinities divided by 2 infinities is 3 over 2. Okay? So that's if the these two have the same degree. Okay? If I have a degree where m is greater than n, m is less than n, I can't use the limit thing. The limit thing really only works with this scenario. When I have greater than, when I start squaring infinity, that starts to not really have, not become a firm concept. Okay, so that's the limit view, and it really only addresses that. Now, my favorite of the three means I don't have to memorize all this stuff, and it's really just thinking about everything in terms of division. All of these scenarios that it's been presented to you so that you have to memorize that summary table, right? That summary table that I wrote out, memorizing that thing. Like, why? First of all, I don't memorize things as much as I probably could or should because I stink at it. I can't memorize anything. It's just terrible how bad I can memorize or fail to memorize things. So if you want, you can think of all this stuff. The vertical asymptote's the same, not going to change. It's just that these scenarios where m is equal to n, m is greater than n, or m is less than n, those are all results of division. So think about this. If I had x plus 2 divided by x plus 3, I'm going to do it long division. Well, what do I multiply this x by to make it into an x? Isn't it 1? This ends up being the quotient. If you prefer, let's do synthetic division. The denominator is x plus 3, so the root is negative 3, and the coefficients are 1 and 2. So I'll bring down the 1. Negative 3 times 1 is negative 3. My remainder ends up being negative 1. So if I look at the division algorithm, x plus 2 over x plus 3 is equal, that's my quotient, 1, plus my remainder of negative 1 over x plus 3. That's my quotient, which, by the way, was my asymptote. It's the horizontal one, y equals 1. If I have a different function, let's say 3 something over 2 something, like I did before, 3 halves, let's prove that it comes out to be 3 halves. So if I have a rational function that is 3x plus 7 over 2x, let's take 3x plus 7, divide it by 2x. What do I have to multiply this 2x by to make it 3x? Well, it turns out to be 3 halves. 3 halves times 2, 3 halves times 2 is equal to 3x. Subtract that, and I get 0. And then plus 7, well, 2x does not divide into 7. It's done. So my division algorithm looks like this. 3x plus 7 over 2x equals my quotient, 3 halves. Look, it's the ratio of the lead coefficients, plus 7 over 2x. Okay? So it is the result of division. By the way, it works that way for all of them. So m is less than n. That's my rational function, right? So let's go clear all this stuff. Let's make some space. And it's going to be x plus 7 divided by x squared plus 2x minus 3. I can't use synthetic division because this is not a binomial. So what do I multiply times x squared to turn it into an x? I can't. There is nothing that'll do that. So my division algorithm ends up looking like this. X plus 7 over x squared plus 2x minus 3 is equal to 0 plus, this is the remainder, over my divisor. Oops, that's minus 3. So this is the quotient because this actually doesn't divide. It's too high a degree. It's like taking 3 and dividing it by 72. 72 can't divide into 3. This has too many degrees. It cannot divide into x plus 7. So 3 divided by 72 is 0 plus the remainder, which is 3 over 72. Any fraction that's less than 1 is a remainder, you could say, of division. So that one is also the quotient, the result of division. Now what about when m is greater than n? That's this situation. Luckily, we can use synthetic division here because I have a binomial, right? And here's the result of division. It should be 3x minus 4 if I remember correctly. So let's use synthetic division. The factor, the 0 for that is negative 2. The root for that polynomial is negative 2. So I have my coefficients of 3, 2, and negative 1. So bring the 3 down. Negative 2 times 3 is 6. Negative 6, that's negative 4. Negative 2 times negative 4 is 8. So that's 7. And so I get, and I believe I already wrote this out previously, this is the result of division. The quotient is 3x 3x minus 4. So my equation is y equals 3x minus 4. Or if I want to look at it in the form of division algorithm, that would be 3x squared plus 2x minus 1 over x plus 2 is equal to the quotient plus the remainder divided by the divisor. There is our asymptote. It's the result of division. So if you want to ignore the whole video and just go, oh, just do the division. Do synthetic when I can. And if I can't, in the situation where this is not a binomial, then I just do long division. Then I don't have to remember all the quote rules. Okay? You still have to do all the other stuff. Vertical asymptote, you need to figure out if it's a removable discontinuity or not. And then you have to determine the location of the graphs relative to the horizontal or slant asymptote. You still have to do all that stuff. I'm just trying to hopefully make it easier to determine the nature of my non-vertical asymptotes. All right, so that's it for rational functions. Good luck.